We saw that quadratic equations in the form of ax squared plus bx plus c equals 0 can be solved for x, providing us with two solutions for x. We also saw, in example 3, that we don't even need to have the c term to be present to get our solutions. What is also true is that we can also get our two solutions if our b or c coefficients are 0. Let's look at x squared equals 36. First, notice that both sides are squared. X squared equals 6 squared. These are a special case. Not every quadratic of this form will have perfect squares on the right side for us to work with. For this case, we can set the equation to 0. X squared minus 6 squared equals 0. We should notice that we have a difference of squares, which can be factored as x minus 6 times x plus 6 equals 0. Using the zero product principle, we can solve each equation for x, giving us x equals 6 and x equals negative 6. What we did is completely acceptable, but we can save steps and time by using the square root to solve this quadratic equation. Recall that the square root of x is equal to the absolute value of x. Looking back at x squared equals 36, if we take the square root of each side, we get the absolute value of x equals plus or minus 6. With the square root tool, if our quadratic equation is set equal to a constant, we can simply take the square root of each side, immediately giving us the solutions. Let's practice with a few examples. Number 1, 2x squared equals 100. Let's first start by dividing the whole equation by 2. X squared equals 50. Taking square roots of each side, we get the absolute value of x equals the square root of 50. So our solutions are x equals plus or minus 5 times the square root of 2. And if that confused you, know that the square root of 50 can be written as the square root of 25 times 2, which equals 5 times the square root of 2. As we can see with taking square roots of constants, we're not always going to receive perfect squares as our solutions. Number 2, 3x squared minus 21 equals 0. Here we have another quadratic that we must simplify before solving. X squared equals 9. This is a very simple quadratic, leaving us with a perfect square solution. The absolute value of x equals 3, or x equals plus or minus 3. Number 3, x squared equals negative 2. We have a very special type of equation here. In order to make sense of this quadratic, we're going to have to recall our work with complex numbers. Taking square roots of both sides gives us the absolute value of x equals the square root of negative 2. Using our rules for negative radicands, we get our solutions of x equals plus or minus I times the square root of 2. Remembering our brief study of complex numbers, it may have seemed strange that we devoted some time to those types of numbers. Even though they don't arise very often in algebra, when they do show up, it's often deep-rooted in core sections, such as here with quadratic equations. As a matter of fact, in many branches of engineering, complex number solutions are often required in solving quadratic equations. Number 4, x plus 1 squared equals 64. In this last example, we might be tempted to expand the binomial and solve it as we've done in the last section. But we can actually take the square root of both sides here, giving us the absolute value of x plus 1 equals 8. Solving for x then gives us x equals 7 and x equals negative 9. This is significantly faster than expanding the binomial, setting the equation equal to 0, then finding factors equal to 0. As we've seen, it is most preferable if we can solve a quadratic equation by using square roots. This is usually the sweet spot, or the simplest and quickest way to solve them. However, there are times when we won't be able to use factors nor square roots to find our solutions. In the next lesson, we'll look at a technique called completing the square that will help us in building a quadratic equation that can be factored.